Hey guys, this is Saptarshi here and welcome to our YouTube channel. Last few classes we have been looking at neural networks, and if you remember that you have the input layer, you have a hidden layer and you have a output layer, right? So this is the most basic form of neural networks, and this hidden layer, we can have multiple of them, right? So if we have multiple of them, then we call such a network as a deep learning based model, and it turns out that such a model has a much better generalization capability. So it can work as a classifier, it can be used in a regression problem, and not only that, they can learn really complex and non-linear decision boundaries. However, because of this large number of hidden layers, there are a lot of parameters, and which makes it more prone to overfitting. Okay, so a set of techniques, a set of techniques which can help curb this tendency is called as regularization techniques, and you can look at last few lectures of ours to learn more about regularization. One other problem is that because of the learning of the weights, so which is one of the main objective of the neural network, okay, which happens based on some optimizer based algorithms, right? So because of this large number of networks, okay, the gradients can really be unstable, okay, and because of that, the training can be slow or the convergence can be really slow or may not happen at all. Weight initialization and batch normalizations are two techniques which are focused to make the training of neural networks more efficient and faster. Okay, so let's now look at the problem of weight initialization. If you remember, okay, that in a standard neural network, so if you have multiple layers, right? So you have a forward pass, okay, where you calculate the actual output and then you see the expected output, you calculate the error, and then you change the weight little bit, okay, and you find the change in the error, so that way you calculate the gradient, okay, and this gradient you actually back propagate, okay, and through this back propagate using algorithms like gradient descent, the weights change or the neural network learns, right? So these weights are very important, okay, but by what weight you should start, right? Will you take any random values? Before that, let's concentrate on one of the tendencies, which is, if you look at the activation function that is generally used is a sigmoid function, okay, and this is the value of the sigmoid, okay, the value of the sigmoid that will typically come from calculating the linear calculating the aggregated values, right, aggregated and activated values, okay, and this is the gradient, right? And if you look at the gradient, right, the rate of change, this becomes very small at as it becomes a large number, both a positive number and a negative number, right? So these are called as saturation region, and probably some good amount of learning happens only in this area, right? And because of this back propagation that happens, what happens is the gradient of the first layer, okay, is multiplied with the second layer, and this process continues. As a result of which, as the gradient is a small number, if it is in the saturation region, okay, so this product also diminishes, right? So as you move to the initial layer, this diminishes, and this problem is called as a vanishing gradient problem, okay, which was a major bottleneck for training neural networks earlier, right? And as a result, the connection weights at the lower layers are almost unchanged and the training never converges, okay. On the other side, this is also possible somehow if the gradient is more than one, right? So similarly, if you continue multiplying from the last layer to its previous layer and so on and so forth, okay, it will multiply or the product will become a large number. So as a result of that, now no question of no convergence, but there will be divergence, right? And this problem is called as a exploding gradient problem. This happens a lot in case of recurrent neural networks, all right? So here is a small example on MNIST dataset, which is very familiar to you by now. So this diagram actually gives you the number of epochs over here, and the average weights of different layers, right? So this MNIST was formed using 3 hidden layers, and you see that this was the third layer, this is the second layer, and this is the first layer. So for all of them, the behavior is similar in terms of the way the weights are getting decayed. However, the weights are getting much more decayed for the first layer compared to the second layer and the third layer. So that is what we are trying to stress over here. So now we have understood that weights has a lot of role to play. Okay, so how do we initialize the weight? So one very simple problem could have been to take a normal distribution of mean 0 and standard deviation 1. Could have worked well, right? So why doesn't it work well? So let's again take a very simple example. Okay, so let's say there are two input variables x1 and x2 which are getting multiplied by w1 and w2 into z. So this is the linear aggregation. Then some activation function is applied and you are getting y. So y can be thought as the activation value, right? So if you just look at z, okay, if you just look at z, so basically you can think that this is actually sum of a normal distribution. So this is one normal distribution, this is one normal distribution, and these are getting added. And it turns out that if you have such mutually independent normal random variables, so if you have, let's say, 100 layers, right, w1 to w100 are different random variables, okay, which has mean of 0 and standard deviation of 1, the composite of this, right, so the aggregation of this also follows a normal distribution. The mean will be 0, but the standard deviation or the variance is going to be sum of all the variances, which will be 100. So what does that mean, right? So that means the activation value, or the z value rather, can be quite varying, right? So it can go quite to the negative axis and quite deep in the positive axis. If that happens, what will happen to the gradients? They will hit in the saturation region, right? So that is one of the problems that we want to avoid over here, right? So if you have, as I said, if you have 100 neurons, then your z can really take very, very large values, right? Okay, so then we will use a normal distribution, but we'll use a variance which is much lower than 1. Then once we sum up, right, so it will not be very, very high. So one simple thing is, the considering the input values, because the number of input values are actually dependent on the number of input nodes that are going to a particular node. So let's understand this. Okay, so let's say that we are trying to find a good variance for these webs. Okay, so if I do that, what I am going to look at is that how many input nodes are coming here, because that many normal distributions or random variables are getting attached with this, right? And how many are going out, right? So this is what we look out. So this number, okay, how many are going out, going in, will be called as fan in, and how many are going out will be called as fan out. So here fan in is 5 and fan out is 4. Okay, and you will calculate fan average, which will be 5 plus 4 by 2, so you will get a 4.5, and you will use this now to control the standard deviation. So you will use a normal distribution of sigma square 1 by fan average, right? So you can understand if the variance is around 1 by 4.5 and there are 5 units, so roughly it will come around 1, right? So that's the basic idea. And instead of a normal distribution, you could have also used a uniform distribution, because uniform distributions will also follow similar properties, that sum of uniform distribution will follow the mean of 0, but the standard deviation will be much higher, right? However, for uniform distribution, you will have to use different range. Okay, you will have to use different range because of its differentiation or difference with normal distribution. Okay, all right. So, if we do not want either the activation values or the gradient values to be uncontrollable, right? So, what we'll do, you will use this kind of normalization techniques, and this is the result from the original paper of the authors, right? So you see that if you do not use, so this is an example where 5 layers are being used, and we are concerned about both the activation values, okay, so which is involved in the forward propagation, and also the derivatives, right, which is applied in your backward propagation. Okay, so if you look at the activation function, you see that the activation function has quite a nice value, quite a less amount of saturation region when you use just this simple weight initialization technique. And the same behavior is almost reciprocated when you are doing that for your gradients, okay, for your gradient. So basically by using your this simple weight initialization scheme, you can get over this problem of vanishing gradient, right? Okay. And in case of ReLU and its variants, okay, as we discussed this for more of tan H and sigmoid, for ReLU the problem becomes little bit different, okay, but however the analogy of the random variables and all still remains. So it turns out that you need to now use a factor of 2 by fan in, okay, you need to use a factor of 2 by fan in when you are dividing the unit variance, okay, and this is often called as He initialization. All right, so now let's look at batch normalization. So you have already seen that we always normalize the inputs, right, so that no one input dominates. So one input can be of value 1 to 10, another can be of value 1 to 1000. Of course the 1 to 1000 will command more weightage, right? So batch normalization actually normalizes the hidden layer outputs, right? So this normalization was happening only on the inputs, okay? But what about the hidden layer outputs, right? So batch normalization tries to do that so that none of the parameters or none of the activation values dominate each other, okay? So this technique consists of adding an operation in the model just before or after the activation function of each hidden layer. So in the original paper, they have suggested adding the activation function at the pre-level. However, it can be generalized and can be applied at the post level also. Okay. So if you add a BN layer or batch normalization layer as the very first layer of your neural network, then you need to standardize your training set. Okay. But to some extent. So we are just going to discuss that. So one of the things that you must notice is that we are talking or telling this as a batch normalization. So why batch normalization? The reason is that we are training the neural network in mini batches. Okay, so we are not looking at the mean and standard deviation of all the observation, but the observations that are in that mini batch, right? So here you are calculating the mean for only that mini batch, and similarly you are using or calculating the standard deviation for that mini batch, and then you are doing this standardization, okay? However, when you are doing the standardization, you are using this your usual epsilon value so that to avoid the divide by zero error, okay? And then finally what you do is you have a new variable, okay, which where you are using two parameters named as gamma and beta. So this gamma actually controls the spread, okay, and this beta actually works kind of like the bias, that how far it is from the zero. Okay, so basically these are two new parameters and can be learned using your backpropagation algorithm, right? So batch normalization does some kind of course a scaling and also a shifting, right? So we will discuss shortly why this shifting is required. Okay, so there is some thing called as a covariate shift. Okay, so let's understand this. So let's say your decision function is something like this red car, right? And these blue lines were what you got from the data. Okay, these were your training samples. However, your test samples comes from a completely different area, and because of you looked at the training samples, you thought that the decision function is like this green line, right? So the thing that we are trying to tell is that there is some amount of difference between the distribution that is used for the training sample and the distribution that is being used for the test sample. Okay, and this is taken from a lecture note from Masashi Sugiyama. So she discusses a lot of reasons for your dataset shift. Okay, so this is a very good read. I recommend you to read that. All right. So there is another way of looking at it. Okay, so just more a visual example. So let's say you have this kind of a training set, okay, where you have all red roses, okay, where so you want to identify whether the picture is of a rose or not. Okay, so if it is a rose, you make y equal to 1. If it is not a rose, you make it y equal to 0. So this is the training scenario, okay, and the testing scenario can be something like this. So you still have roses, right? But you have different color roses now coming up. So there is a shift that is happening. Now, what is the relation of this covariate shift with our batch normalization? So the mini batches that are there, what is happening is that there can be a little bit shift because you are calculating the mean and the standard deviation on a mini batch, right? So when you take another mini batch, there can be little bit of a difference, right? So this gives a result of a covariate shift, and your batch normalization can solve this problem as well, apart from this domination problem of the activation units. All right. And finally, some other advantages. Of course, the vanishing gradient problem is strongly reduced that to the point they could use saturating activation functions such as tanh, even the logistic activation function. So if you use a batch normalization, you can use these activation function as well. The networks also were much less sensitive to the weight initialization. So batch normalization is strong enough to not require any weight initialization technique also, right? So these actually came quite later than the weight initialization techniques, and reportedly with batch normalization, we are able to use much larger training rates, right? So if you have larger learning rates, what will happen is that will be significantly speed up the learning process, and it also acts as a regularization. So you can look at some of the research papers where you can see that if you have used batch normalization and have not used batch normalization and used dropout, you have kind of similar result, or in some cases you have even got better result using batch normalization. So these are some of the advantages of batch normalization, and that is the reason it is a very important technique to know. Okay, thanks guys for watching these videos. Thanks for your encouragements, and please give your questions in the comment section, and give your like and subscribe generously. Thank you so much, guys.